This lesson will talk about the exceptions to the octet rule. So far we've a great deal of time practicing drawing structures so that every atom other than hydrogen achieves the octet. But here we will consider three scenarios, three situations that will occur that allow us to break the octet rule. And typically they're going to be driven by the overall concept of formal charge. If we can alleviate a formal charge by breaking the octet rule, we will indeed do so. The first of those three situations deals with a very rare, a rare situation, but sometimes it will occur, where ions or molecules form, but they have an odd number of electrons. And if I end up with an odd number of valence electrons, we can clearly see somebody's going to not have a partner and end up with the magic number of 8. So if I have an odd number, automatically rule breaker. Second scenario is sometimes the central atom will have less than an octet. So a number where the number around the central atom either can be something other than 8, perhaps it will be 6, perhaps it'll even be 4. So something smaller. And then we'll take a look at a third scenario where we have more than 8 electrons around the central atom, and that's called an expanded octet, where I can put in more than 4 attachments around the central atom. So odd number, sometimes we have fewer than 8, sometimes we have more than 8 electrons around the central atom in an ion or molecule. Let's consider each one of these one at a time and provide some examples. So the first scenario is if we have an odd number of electrons. And let me just model quickly with 3 examples and just thinking about how they might pair up. So ClO2. How many valence electrons would this molecule have? Well, chlorine would have 7. Oops. So here we'd have 7 from the chlorine. Oxygen has 6, but there's 2 of them, so the total here is 12. 7 plus 12, well, that would give us 19 valence electrons. That's an odd number. Somebody's going to be without a partner. Here's NO2. Nitrogen, of course, has 5. Oxygen has 6, but there's 2 of them there, so we'd have 17 valence electrons in this particular structure, another scenario where somebody would be left without a partner. NO2, a third example, oxygen with 5 would give oxygen 6, but there's 2, so this this 17 here, this of course NO, I hopped right over mathematically, NO would look like 5 plus 6 is 11, so I did that one structure. So we have 19, 11, or 17, all of these scenarios giving us an odd number, and perhaps it's worth just drawing one quickly to see what it would end up looking like. Let's just take a quick gander at ClO2. Chlorine, of course, would go in the center, the least electronegative element. We'll place the oxygens attached back to it. So what have we accomplished so far? We said our starting number was 19 electrons. We've used 4, giving us a remainder of 15. Now we go ahead and put the octet on everybody but the central atom. So I place 6 dots around each of the oxygens. And that used up 12. We have 3 left. 1, 2, 3 on the central atom. No dots left. You can clearly see how unstable or very reactive this molecule would be. So not a configuration that it would be happy with. It definitely would react to create a more stable arrangement. Sometimes you'll have molecules with odd numbers. Our second scenario, sometimes we will have fewer than 8 electrons. Fewer than 8 electrons. Well, here's a situation where we have BF3, boron trifluoride. Boron trifluoride is a molecule which will break the octet rule simply because the boron itself has fewer than 8 electrons. Let's kind of take a look at this and we'll draw it together. Let's just scroll up and start from scratch. BF3. Boron lives in group 3A. It has 3 valence electrons. Fluorine lives in group 7A, has 7 valence electrons. There's 3 of them. So we're going to come up with 24 total valence electrons in this molecule. 24 dots, no more, no less. The least electronegative goes in the center, and we attach back to it. And how many have we used so far by creating this structure? We've used 2, 4, 6. That leaves us 18 dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. No dots left. So we have a scenario, no dots. So now it would suggest, if we were following the octet rules, that's my clue that this central atom does not have 8. So we'll be tempted to place a multiple bond on it. But pause a moment with me and consider what that would do. Boron, who lives in group 3A, 3 valence electrons, has 1, 2, 3 electrons associated with it. Remember, half of the bonded pair? Right now, boron has a formal charge of 0. Ideal, isn't it? Fluorine lives in group 7A, 7 valence electrons. Right now, it has 7 electrons associated with it. Formal charge is 0 on every one of these fluorines because they're identical. If I leave this boron trifluoride as it is, all singles, no multiple bonds, every atom now has a formal charge of 0. Ideal. But if we had gone up and started to create the multiple bonds, we would start to see, and again, these are all in residence. Remember that term from our previous lesson? Any of those fluorines is an equally valid choice. The double arrow says we have a resonance possibility. If I had satisfied the octet to the central atom boron, I start to develop formal charges. I have a formal charge of +1 on a fluorine, a -1 in the center. Notice that the fluorines in every one of the possible resonance structures has a +1, and the central atom here always with a -1. Well, that's not ideal. It's not an accurate picture of the distribution of the electrons. And our reasoning is that, based on formal charge, had I left the structures with all single bonds, even though this boron in the center had only 6 electrons, all the formal charges are at 0, and that indeed will dominate my selection of the correct choice. I'm going to allow boron, who lives in group 3, to only have 3 valence electrons, half of those in the bonded shell, to keep its formal charge at 0. The correct structure for boron trifluoride breaks the octet rule so that I alleviate formal charge. In this slide, we see the most important structure here with all of the formal charges at a 0, just as we had drawn. 3 minus 3 gave us 0. 7 minus 7. Remember our formal charge calculation? Valence electrons. What group does it live in? Minus the assigned electrons. So there's my calculation for formal charge. Boron lives in group 3, 3 dots assigned, formal charge of 0. And every time we went through here, we developed formal charges. Those are not the correct structure. When we have a situation where filling the octet of the central atom results in formal charges, don't do it. Don't do it. Break the octet rule. If you end up creating formal charge where we have a negative charge on the central atom and the positive charge on the more electronegative outer atoms, please break the rule and keep formal charges to a minimum. when filling the octet of the central atom results in a negative charge on the central atom and a positive charge on the more electronegative outer atom, which was fluorine here, don't fill the octet of the central atom. Break the rule. Situation number 1, we started the lesson. Sometimes we have an odd number of electrons. No way will they have 8. Somebody will have no partner. Situation number 2, sometimes if formal charge dictates, the central atom will have fewer than 8 electrons, such as in boron trifluoride. The third case, sometimes we have to expand the octet and place more than 8 electrons around the atom. In this model, let's take a look at PCl5. Presumably, the only way phosphorus can attach 5 ligands around it is to expand the octet. Now, when this occurs, we have to have some room in the d orbital to expand the octet. And this is one of those cases where the d orbital actually becomes part of the electrons that are involved in bonding. So they must have a d sublevel in order to expand the octet. So not only can the s and the p's be involved in bonding, but now the d subshell is involved when we expand the octet. Atoms that do not have d sublevels, are too small, will never expand their octet. So let's take a peek. Let's take a look at what we've got. PCl5, draw it with me. Phosphorus has 5 valence electrons, lives in group 5a. Chlorine has 7. 7 times 5 is 35. This entire structure will have 40 valence electrons by the time we're done. 7 times 5, 35. Phosphorus is the least electronegative. It's the one we have just one of. How can I possibly attach 5 chlorines back to it without expanding it? Usually we see 4 dots going through, don't we? 1, 2, 3, 4. Here's each one of the chlorines. But I have a 5th one to place. Remember, they have to go back to the central. I can't attach a chlorine to another chlorine. It makes no sense. So I expand the octet and I place the 5th chlorine on it. So right away, I've already got 5 things attached to the central atom. That tells me I have 10 electrons around the central atom, giving me 30 left over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. No dots left when I complete the octet. Phosphorus lives in group 5a, 5 valence electrons. It has 1, 2, 3, 4, 5 associated electrons, 1/2 of each bonded pair. Phosphorus has a formal charge of 0. You can clearly see the advantage of phosphorus expanding the octet to alleviate the formal charge. Chlorine lives in group 7a, 7 valence electrons. It has 1, 2, 3, 4, 5, 6, and half of the bonded pair. It also has a formal charge of 0. Every one of them has a formal charge of 0. This clearly is an ideal Lewis dot structure. By expanding the octet, we place 5 chlorines around the phosphorus, which it's fine to do because now we've dropped a formal charge of phosphorus to 0. An ideal scenario. Phosphorus pentachloride expanded the octet into the d orbitals, giving us a molecule with greater than 8 around its central atom. If we had not expanded the octet, sometimes we'll see structures where we have formal charges develop. Shall we try one together? Let's try one together. I'll scroll down. We'll say, let's draw for the polyatomic ion called phosphate. This actually is the top of page 8 if you're looking at your notes. PO4 carrying a -3 charge, the polyatomic phosphate. Let's take a peek at following the rules and drawing this particular structure. All right, let's count dots. Phosphorus has 5 valence electrons. Oxygen lives in group 6. 6 times 4 is 24. We have 3 extra, notice the charge, 3 extra electrons we get to place. 27, 28, 29, 30, 31, 32 dots by the time we're done. Phosphorus goes in the center. It's the least electronegative. We'll attach the central atom, attach back to the central atom with each of the oxygens. Let's bookkeep. 2, 4, 6, 8 electrons were used. That gives us 24 remaining electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. No dots left. One possible correct structure, put it in a bracket, it's a polyatomic ion. So here's one that follows all the rules. Everybody has 8 electrons. You might think everybody's peachy. But consider formal charge. Phosphorus lives in group 5A. Phosphorus lives in group 5A, 5 valence electrons. It has 1, 2, 3, 4 electrons associated with it. It has a formal charge of +1. Oxygen lives in group 6A, 6 valence electrons. 1, 2, 3, 4, 5, 6, 7 electrons assigned to it. Oxygen has a formal charge of -1. Every one of them has a formal charge of -1. They're all identical. So is this an ideal Lewis dot structure, or can we rearrange to alleviate the formal charge on the central atom phosphorus? Well, suppose we took one of the, and again, it wouldn't matter because of resonance. They're all equal but different atoms. Suppose I just have to pick one. I pick a set of electrons from an oxygen and create a double bond. If I were to redraw that structure, still a single bond to each of these, but a double bond to one of the oxygens, leaving it with simply 2 unbonded pair. Draw them in. All of the dots are important. What have we done to the formal charge of our central atom? And again, I have to put it in a bracket, the -3 overall charge. Alrighty. Well, now when I consider formal charge, phosphorus lives in group 5A, 1, 2, 3, 5 valence electrons. It now has a formal charge of 0. Oxygen, who lives in group 6A, 1, 2, 3, 4, 5, 6. This particular oxygen that we placed a double bond has now gotten a formal charge of 0. These oxygens will remain at a formal charge of -1, but look what's happened. The overall formal charge equates the charge on the polyatomic ion, and the negative is on the more electronegative element. Very important details that lets me know this indeed is the correct structure. By expanding the octet on phosphorus, I brought down its formal charge, not only on the phosphorus but also on one of the oxygens, where the net remainder formal charge equates the overall polyatomic ion charge. We drew the structure that alleviated the positive charge on the central atom, phosphorus, brought it down to 0. We alleviated one of the formal charges on oxygen. Now we would not keep going because then we would start to create a negative formal charge on the phosphorus. This indeed is the best structure. By expanding the octet, we alleviated formal charge. What have we learned? We've learned that there are situations where that more than one structure exists. We saw that with phosphate. The lesson we need to walk away: when the central atom is on the third row or below, third row on the periodic table, period 3. Expanding its octet eliminates formal charges. Do so. It has to have access to d orbitals. Now remember, the first time in our electron pyramid, this kind of makes sense of what this is saying. 1s, 2s, 2p, 3s, 3p. Oh, in the third energy level, there's finally some d sublevels that we can use to expand the octet to alleviate formal charge. So they're out there and available. Phosphorus has access to the 3d orbitals. It would normally place them there. It expands to create room for more bonding around the central atom. So it has to be in period 3, where n equals 3 on the chart. Period 1, there's no d orbital access. Period 2, there's no d orbital access. Period 3 or greater, in order to expand the octet, and do so if it eliminates formal charge.